Problem 1.4 is our first exercise for normalization. We are given a wave function psi of x comma 0 is equivalent to a piecewise, where from 0 to a, it is equal to a times x divided by a. From a to b, it is equal to capital A times b minus x divided by b minus a, and it is equal to 0 for any other value. And then we have a, and little b are all positive constants. So part A, our first job is to normalize our wave function psi, which is to find big A in terms of little a and little b. So let's start with that. And we know that under normalization, what we require is that the magnitude of psi of x comma 0 squared with an integral over all of space, which in 1D is just from negative infinity to positive infinity, must equal 1, because the maximum probability is 100% or 1. So we can do that with this. Since this is a piecewise function, we have to split this into two different integrals. So we have to say that we get the integral from 0 to a. Actually, it might be easier to visualize this if we use two different colors. So the integral from 0 to a of a squared times x squared over a dx, or a squared dx. And then we add on our second piecewise integral, so the integral from a to b. Same thing, a squared times b minus x squared divided by b minus a squared dx. And this whole thing must equal 1 in order to be a valid probability distribution. So we can start by sort of moving our constants out of our integral. So we know that a squared times integral from 0 to a, and let's just start with this left side. So a squared times integral from 0 to a of x squared divided by a squared dx. We can move the a squared out as well. Then we get a squared times 1 over a little a squared times 1/3 x cubed, and then set our integrand limits from 0 to a. So therefore this equals a squared times a over 3. Okay, now we can do the same thing with our second integral. So we move a squared out to the left, integral from a to b this time of b minus a squared, or b minus x squared, divided by b minus a squared dx. And here we can sort of expand this into a polynomial and integrate it afterwards. So we will do the same thing and move the 1 over b minus a squared outside of our integral, because that's just a constant. So that gives us a squared times 1 over b minus a squared times our integral from a to b of b squared minus 2bx plus x squared dx. Where what I've done here is I've just expanded my b minus x squared into a polynomial, so b minus x multiplied by b minus x, and that gives me this. Now I just have to integrate this in full, so then this gives me a squared times 1 over b minus a squared, and then we integrate each term individually, so b squared times x minus bx squared plus 1/3 x cubed and we set the bounds from A to B. And from here, we just sort of have to plug everything in, and I won't bother with the math here just to save some time, but this should end up canceling into a squared times b minus a, all divided by 3. So what we get is that our first integral, which equals a squared, it's a little bit small, first integral a squared times a divided by 3, added with our second integral, which is a squared times b minus a divided by 3, must equal 1. So let's sort of just add terms together. So this becomes a squared, where we distribute out a squared onto the left side, and then we take our interior, so that's a added with b minus a, and all of that divided by 3, because everything shares a common factor. This equals 1, therefore a squared times b over 3 equals 1. Our job now is just to isolate a, which is a very simple process, and then we take the square root of everything, and we get that a is equivalent to the square root of 3 divided by b. So we have finished part A, and we have found out what our normalization constant A is required to be. Now, for part B, our next job is to sketch our wave function psi of x comma 0 as a function of x. So I've written out our piecewise function in terms of A. I've left out the 0 component, which is outside of our intervals of interest, because that doesn't really matter to us. We don't particularly care about areas where the psi function has a probability density of 0. And we now want to plug this onto a graph, sort of. So one way to just kind of know what the graph is supposed to look like just by looking at our equations is we can recognize that a and b are constants. So a and b are constants. And because of that, we can sort of combine them together to form another constant c. So in this way, one thing we can do is we can rewrite our functions. We can say that from 0 to a, which has the psi function of square root of 3 over b times x divided by a, we can rewrite this and say that this is equal to square root of 3 divided by a times square root of b. I'm just rewriting it to make it neater, and then all of this multiplied by x. So square root of 3 divided by a times square root of b, square root of 3 is a constant, a is a constant, b is a constant. So what we can do is we can say that, okay, well, we can define a new constant c which equals this. So this is proportional to just some constant c times x. And if we think about that, well, if we define this function to be from 0 to a, what this means is that on our graph, where let's say that this is a, it will look something like this, where there is some sort of linearly increasing line that goes up, that slopes upwards to a. In the same logic, down here we have square root of 3 over b multiplied by b minus x divided by b minus a. So the first thing we can do is we can say that, well, we can sort of split this apart into multiple terms. So we have square root of 3 over b multiplied by 1 over b minus a multiplied by b minus x. And this entire term at the front here, square root of 3 over b times 1 over b minus a, this is just one big constant. So we can let's call this constant d. So this is equal to d multiplied by b minus x. And if we use distributive property, well, d is a constant and b is also a constant, so we can combine them together, and let's just call that e. So this equals e minus d times x. And E and D are both constants, so this also takes on the form of a linear line, except instead of sloping upwards, it slopes downwards. So if we graph this, it will look something like this, where this is A, and this is B, and this is where our second function is defined. This is the interval where it's defined. And what we have is that, let's say that this is equal to E, and from this point, it's sort of, our graph sort of looks like this. Let's say. And as it turns out, since it's only defined starting at A, we can sort of just erase the points up here and the points down here, which are outside of our interval of interest, and we can write out our solution to look something like, whoops, that is not a very good line. Write out a solution to look something like this. So we can sort of combine these two, and we'll realize that the combined wave function solution ends up looking something like this, where this is A and this is B. And we have a wave function which goes up to this point, slopes upwards up to A, and then slopes downwards to B. So effectively what this is just a triangle, and our wave function probability density is therefore a triangular shape. And as we change our parameters A and B, what will happen is our triangle will also change shape. If we make A really big, then this red leg will become really large compared to the blue leg, etc., etc. In part C, we now want to know where the particle is most likely to be found at t equals 0. So in B, we sort of confirmed that the wave function, when graphed out, looks like a triangle. So to find the most probable position that the particle is going to be in, that's just a matter of finding what point along this graph does psi have the highest magnitude. And since this is a triangle, the answer should be obvious, hopefully, that the highest probability is directly at sort of like the middle, the vertex of this triangle, where the upward slope meets the downward slope. And that happens exactly at A. So we can sort of say that for part C, we can sort of just say that the maximum probability occurs at x equals A. And what we're effectively saying is that given our initial wave function psi of x comma 0, we are most likely to find our particle in a position close to A. In part D, we want to find the probability of finding the particle to the left of A. And we want to check our result using two limiting cases where B equals A and B equals 2A. So the first thing we should do is sort of set up our integral. So in part D, one thing we know is that to the left of A, so from 0 to A, we have psi of x defined using this following function, square root of 3 over b times x divided by A. So what we can say is we know that the probability of finding x to the left of A is equal to the integral from 0 to A, not A, from 0 to A of the magnitude of psi x comma 0 squared dx. And as it turns out, in part A, we actually already solved this. We know that this equals a squared times a divided by 3. So let's write that out right now. So we know that this equals a squared times a divided by 3. Let me just make sure that this is correct. Right. So this is the probability of us finding our particle to the left of A. And we solve for a squared. We know that A, in fact, equals square root of 3 divided by b. So a squared is just equal to 3 over b. So we plug this in. So this equals 3 over b times a over 3, which then equals a over b. So this is sort of our probability of finding the particle to the left of A. Now our goal is to check this for two different scenarios. So limiting case 1, A equals B. And if we were to sort of graph both of these piecewise functions on Desmos and then set A equal to B, what we will find is this following function. So let's just move this up here. So if we graph this on Desmos, what we'll find is that if A is equal to B, what will actually happen is the entire downward sloping section of our function will actually just completely disappear. We can check this just by looking at sort of our graphs here, our piecewise function graphs that we got from part B. If B is equal to A, then we get A minus X over A minus A over A. And this sort of just no longer makes sense because this becomes sort of infinity, and also the interval just becomes 0. So it doesn't really make sense to have this sort of downward sloping section anymore. So if A is equal to B, then our probability becomes P is equal to A over A, which is just equal to 1, which implies that there is a 100% chance of finding the particle to the left of A. And that makes sense here because the interval of the probability from A to B has completely disappeared. So therefore, X equals A is actually the maximum possible distance that the particle can be in. And there's a 100% chance of the particle being to the left of it because it can only be to the left of it since A is now sort of the rightmost limit for our probability density function. Now, let's do the same thing and just define limiting case 2. A equals 2B. And same thing, if we sort of take our two equations, square root of 3 over A square root of B times X, and square root of 3 over B times 1 over B minus A times B minus X, and we plug B equals 2A into this, what we will get is an isosceles triangle. Where the two sides, the upward sloping side and the downward sloping side, are exactly equal to each other. So if we plug this in, then what we will get is that P is equal to, as above, A over B, or A over 2A, which therefore equals 1/2. And this also makes sense because our triangle is perfectly symmetrical. So if we split off at A, which is the right in the middle of our triangle, then half of the area is exactly to the left and half of the area is exactly to the right. Therefore, the particle has a 50% chance probability of being found to the left and a 50% chance probability of being found to the right. The final part of this problem is to find the expectation value of X. And we sort of already know how to find the expectation value of certain quantities. We know that the expectation value of X is simply equal to the integral over all of space, so from negative infinity to positive infinity of X times magnitude psi x0 squared dx. And we sort of already have our two integrals here, so let's just take these and copy them. Put them here. So this equals, and then we're going to attach an x to each of these terms because the x distributes in, and then we get rid of, because it no longer equals 1, we're now finding the sort of expectation value of X, not the total probability anymore. And now it is just a process of just redoing these integrals with an extra X in front multiplied onto everything. So I will not, sort of in the interest of saving time, I'm not going to bother actually doing these integrals because the process is mostly the same. For this one, this is just an x cubed integral because a squared over small a squared moves out and we can just solve it as it is. It's kind of trivial. And then this right one, we once again expand b minus x squared into a polynomial add x onto each term, or multiply x onto each term, and the process of solving is once again also trivial. And finally, once we do this and plug everything in, we should find that the expectation value of x is in fact equal to 2a plus b, all divided by 4.